Last lecture, we took a trip to visit the million-year-old universe, to take in the sights, at least in our mind's eye. We found a slowly changing rainbow sky, an exceedingly thin, slightly foggy hot atmosphere, and everywhere brilliant light, as bright as hovering over a star's surface. Now here, within the Earth's atmosphere, we're constantly aware of sound waves coming from all directions. Were there sound waves in the primordial atmosphere of the young universe? The answer is yes, there were, and they're going to be the subject of this lecture and the next. Now, quite apart from the delightful prospect of actually listening to primordial sound, there are a number of reasons cosmologists are interested in Big Bang acoustics. And the primary one is that the sound an object makes tells you a great deal about its nature. So by studying primordial sound, you can actually measure many important properties of the universe, and we'll look at how this is done in the next lecture. But in this lecture, we're going to look at the nature of the primordial sound itself and how it's generated. Now, sound waves inherently involve slight variations from place to place. So primordial sound also provides our first indication that the universe isn't completely smooth. And as we'll learn in lecture 17, over time, the sound waves grow to form the first stars and galaxies. So they act as a crucial bridge from the smooth young universe to the lumpy adolescent universe. So these next two lectures will also set the stage for Theme 4, which is all about the formation and evolution of galaxies and the galaxy web. So let's begin with the nature of sound. This little animation shows sound waves coming from a tuning fork. The wave peaks are where molecules bunch up in compressions, giving a slightly higher pressure. The wave troughs are where molecules are further apart in a rarefaction, giving a slightly lower pressure. The pattern moves along a bit like a crowd surge. Molecules bash their neighbours, who bash their neighbours, and so on, and so on. As you might imagine, from this crowd surge metaphor, the speed of a sound wave is similar to the speed of the individual molecules. For example, the speed of sound in air is about 750 miles per hour, which is similar to the 1,000 miles per hour of a typical oxygen or nitrogen molecule. Here's a bit more terminology. The distance between two peaks is called the wavelength, and the number of waves that pass by per second is called the frequency. It's measured in hertz, which are really waves per second. Now, wavelength and frequency are complementary. So big waves have small frequencies and small waves have big frequencies. Now, there are three important properties that sound has that we need to consider. First is loudness, which depends on the ratio of pressure variations, that's peak to trough, compared to the average pressure, which I've written as delta P over P. It's measured in decibels, going from deafening to noisy to quiet is 135 to 75 to 15 decibels. And these have pressure variations of about 1,000th, 1,000,000th, and 1,000,000,000th of an atmospheric pressure. So these are tiny variations. Human ears are very sensitive and can cope with a huge range of pressure differences. Okay, next is pitch, which depends on frequency, the number of waves that pass by your ears per second. Deep. That's about 200 waves per second. Deep. That's about 600 waves per second. Concert A, for example, is 440 hertz, while 220 hertz is an octave below, and 880 hertz is an octave above. Normally, humans can hear sounds with a pitch somewhere between about 20 hertz and 20,000 or 20 kilohertz. Now, the third property of sound is its quality. Why does A440 played on a piano sound different from A440 played on a violin? Each has a strong 440 hertz component, but many other frequencies are also present. In fact, almost all sounds have many frequencies present simultaneously, and the best way to show them all is using a sound spectrum. Now, sound spectra are going to be important in these lectures, so let's take a moment to get familiar with them. Here's the sound spectrum of a flute playing a single note, and here's the note itself. Along the bottom is frequency, with low frequencies, low pitch, on the left, and high frequencies, high pitch, on the right. The numbers here are kilohertz, or thousands of hertz. And up the axis is loudness, in decibels. So all sounds have a spectrum with many pitches present, with some louder than others. Now, in the case of this musical note, there is a very clear pattern made from a set of almost pure tones. There's a strong fundamental, which our ears hear as the primary pitch, and a set of higher harmonics. This is, in fact, typical of many resonant systems. They have a number of specific ways of vibrating, each with its own frequency. Resonant systems are things like stretched strings and columns of air in musical instruments, or objects with well-defined boundaries, like a wine glass or a drum skin. Let's now play the same note, but on a clarinet. The subtle difference in sound is because the relative strengths of these harmonics are different. The difference, in turn, depends on the different structure of the flute and clarinet, and would be different again for a bassoon or a piano. The other more general category of sound is noise, wind in the trees or a waterfall. These sounds have a wide, continuous range of pitches, and here's an example of a broad, smooth sound spectrum with little or no structure, and here's its sound. Now, in a minute, we'll learn that the primordial sound has a quality somewhere between a musical note and noise. But first, let's return to the young universe and try to see how sound waves can be present. Now, first of all, you must please forget what you may have learned as a child, that there is no sound in the vacuum of outer space. Last lecture, we learned that in the young universe, all matter was spread out evenly in a sort of atmosphere. Now, it was extremely thin by human standards, but nevertheless, sound waves could move in it. Let's be a bit more specific. At 100,000 years after the Big Bang, each cubic centimetre contained about 2,000 protons and electrons, and about 3,000 billion photons, all at 6,000 degrees. It's a hot, thin, brilliant, foggy gas. Now, the fact that the gas is foggy means that all three components are tied together. All particles are bouncing off each other and behave as a single gas. Cosmologists call this a photon-baryon gas. Baryon, you may remember, is just a fancy word for the atomic constituents, protons, neutrons, and electrons. You might think of the multi-component gas a bit like our own atmosphere, where the oxygen and nitrogen molecules are intimately tied together as a single gas. Now, if we're interested in sound, we need to ask what the pressure of the gas is. See, pressure is the force that particles make when they hit a surface, like rain striking a window pane. Each drop pushes on the window. Ultimately, it's this force that makes the gas move back and forth from peak to trough in a sound wave. Now, it turns out that the pressure of a gas depends only on two things: its temperature and how many particles there are per cubic centimetre. And perhaps surprisingly, for any given temperature, it doesn't matter what kind of particle. It could be a proton, electron, or even a photon. They all contribute the same pressure. And this leads to some rather remarkable facts about the primordial gas. First, because photons of light far outnumber all the other particles, they also provide almost all of the pressure. And this seems a little unusual or strange to us. We don't normally think of light beams, like flashlights, as things that push, but they do, just a tiny bit. And when the light is brilliant and the atoms are rare, then light can dominate the pressure, as it does in the young universe. Secondly, the actual pressure in the primordial gas is very low by human standards, about 1/1,000,000th of our atmosphere's pressure. And thirdly, since it's light that provides the pressure, the speed of the pressure waves is incredibly fast. Remember our crowd surge metaphor. Pressure waves move with roughly the speed of the particles. And in this case, the particles are photons moving at light speed. So the speed of sound waves in the primordial gas is about 60% of the speed of light. So, summarizing, we have an extremely lightweight, foggy gas of brilliant light and a trace of particles, all behaving as a single fluid with a modest pressure and very high sound speed. With light dominating, you can also think of the primordial sound waves as great surges in the brilliance of light. Now, with this background now in place, how do we observe the sound waves in the young universe? Well, here's our cleaned, stretched image of the microwave background, showing the famous patchiness. You can think of the patches as the sum of many waves, like these water waves, but instead of water height, the waves are of higher and lower pressure. These are sound waves, caught and made visible as they cross the wall of fog that is the microwave background. The reason we see them as brighter and darker microwave emission is that regions of higher and lower pressure also have higher and lower temperature, which in turn makes the gas glow brighter and dimmer. So, patches on the microwave background are the peaks and troughs of sound waves made visible because the gas is glowing. So, let's now figure out what the primordial sound actually sounded like. First of all, finding its loudness is easy. The variation in brightness, which is roughly 1 part in 10,000, tells us more or less directly what the variation in pressure is, delta P over P. Even though these variations are very slight, they correspond to about 110 decibels. That's about as loud as a rock concert. Front row seats at Pink Floyd. It seems delightful to me that the primordial sound is neither disappointingly quiet, and nor is it fatally loud. It's just viscerally powerful. Now, finding pitch is actually also pretty easy, because we know the distance to the microwave background. And so we can convert the angular size of the patches on the sky to their physical size in light years. So we have their wavelengths. Now, typical primordial sound waves are between 40,000 and 700,000 light years long. So these are huge waves. And since we also know the speed of sound, that's 60% of the speed of light, we can figure out their frequency. So a typical sound wave may take 100,000 years to pass you by. So the primordial sound is way too deep for us to hear. Not even a single wave would pass by you during your entire lifetime. There's actually a simple reason the primordial sound is so deep. The universe is so big. just as larger air pipes make deeper notes, the universe's organ pipes are roughly the horizon size, huge. So not surprisingly, they make very deep notes, roughly 50 octaves below our normal range of hearing. So let's now look at how primordial sound is generated and then sustained. Now, you may think this is a bit of a non-question. Well, there was a big bang, and the explosion must surely have been very loud. Well, this is completely wrong thinking. The Big Bang was not an explosion into an atmosphere. It was an expansion of space itself. In fact, the Hubble law tells us that every point recedes from every other point. No compression, no sound. Paradoxically, the Big Bang was totally silent. So how does the sound get started? Well, in lecture 32, we'll learn that although the universe is born silent, it was also born very slightly lumpy. On all scales, from tiny to huge, there were slight variations in the density of all components. Randomly scattered everywhere, a sort of three-dimensional mottle of denser and less dense regions. But, and this is important, the uneven dark matter and uneven photon-baryon gas behave quite differently. The dark matter clumps basically stay in place, while the photon-baryon gas, because it has pressure, bounces in and out of the dark matter clumps, making sound waves. This shows a bit more detail. Here's a region where the dark matter is a little denser. Now the gas feels the dark matter's gravity, so it begins to fall towards this denser region. Soon, though, its pressure is higher, and this halts and reverses the motion, pushing the gas back out. Now this time it overshoots, only to turn around and fall back in again. The cycle repeats, and we have a sound wave. You can think of this denser region a bit like a spherical organ pipe into which gas falls and bounces in and out. Now, of course, there isn't just a single denser region. There's a whole range of dark matter clumps of all sizes and all shapes. And so, in a sense, there is an entire register of organ pipe sizes. We seem to have an entire musical instrument here with a wide range of possible sounding notes. So this brings us to our next important question. What is the primordial sound spectrum? Which of these organ pipes is sounding and which are not? So let's start with the microwave background patchiness. You can think of this image as being made from the sum of a few very long waves of low frequency, many medium waves of medium frequency, and many small waves of high frequency, all added together. Each sized wave contributes a particular part of the sound spectrum. Now, using a clever computer program, it's actually possible to disentangle all these waves and see how much there is of each size, how loud each pitch is. The resulting sound spectrum is called C of L, where C is the loudness and L is the frequency. Basically, big patches on the microwave sky have a small L, and small patches on the microwave sky have big L. And here's the amazing result, which includes the best data as of about 2006. And the line is a theoretical computer model, which we'll talk about later. It looks like a cross between a noise spectrum and a musical instrument spectrum. It has an overall broad shape, but with an unmistakable fundamental and harmonics. This has got to be one of the most stunning results from modern cosmology. It's the birth cry from the young universe. Well, to make this audible, we need to add all these tones together and shift up by about 50 octaves. And to do this, I've simply made the L value of patch frequency into hertz. So the first peak falls close to 220 hertz. That's the A below concert A. Let's play that sound now. And remember, to be authentic, it needs to be at rock concert volume. So here it is. Well, I'm not sure what you made of that, but it's certainly more noise-like than musical, a sort of deep roar. But perhaps the most bizarre feature of primordial sound are those harmonics, specific tones, roughly equally spaced in pitch, that stand out. What makes those? Now, for musical instruments, harmonics arise because the vibrating system is bounded in space, allowing exactly 1 or 2 or 3 or any whole number of waves to fit within the boundary. But the universe has no boundary, so why the harmonics? It's because the universe is bounded in time. Between the Big Bang and the microwave background is 400,000 years. During that time, the gas is busy falling into and bouncing out of a wide range of dark matter organ pipes. For the smaller ones, there's been time for several oscillations, while for the larger ones, there's only been 1 or 2. Now, there is a largest region into which the gas has just fallen for the first time. These regions have maximum pressure contrast, and they show up as the fundamental, about 700,000 light years in size, 1 degree on the sky. Now, there's also a somewhat smaller region size, where the gas has fallen in once, bounced out, and fallen in for the second time. These sized regions show up as the third peak. Now, likewise, there's a whole sequence of ever smaller regions where the gas is just arriving at the bottom for the third, fourth, and fifth time. And these yield the fifth, seventh, and ninth harmonic peaks. See, the odd harmonics are called compression peaks because the gas in the dark matter regions is compressed. Now, there's a whole set of intermediate-sized dark matter clumps where the gas has just bounced out at the time of the microwave background, leaving a rarefaction, an under-pressured region. In fact, the second, fourth, sixth, and eighth harmonics arise this way. So the even harmonics are called rarefaction peaks because the gas in the dark matter regions is in the rarefaction part of its cycle. So ultimately, dark matter clumps with just the right size to be caught at the time of the microwave background at either a maximum compression or a maximum rarefaction exhibit the strongest patchiness. And so these sized regions appear as peaks in the sound spectrum. It's perhaps disappointing that the sound isn't more musical to our ears, especially since it contains these harmonics. So let's look at why that's the case. First of all, the microwave background patches include several contaminating effects, and they only approximate the true sound. One way to access the true or pure sound uses a computer to calculate the sound in the young universe. Now, we'll talk more about these computer simulations next lecture, but here you can see the sound spectrum of this pure sound, which cosmologists call P of K. Well, does the cleaner set of harmonics seen in the pure sound, P of K, make a more musical sound? Let's see, by alternating between the two. Well, to my ear, the pure sound is a little cleaner, but it's still far from musical. The main problem is that the primordial harmonics are broad, and our ears hear this range of frequencies as noise. This is actually very obvious if we use a decibel scale to compare the primordial and the flute spectra. The flute harmonics are so much narrower. Listen to the difference. Now, at this point, we can actually have a little bit of fun and artificially make the primordial harmonics narrow to see what a musical version of the sound would be like, keeping their pitch and relative intensity the same. Here it is. It has a rather eerie quality, containing an interval between a musical major third and minor third, something one rarely comes across in Western music. Okay, what about the primordial sound at earlier times, before we see it on the microwave background? You see, we can't actually access this sound observationally because we would need us to look deeper into the fog. But what we can do is use those computer simulations to recreate the sound. Now, in this next example, those 400,000 years are compressed into just 10 seconds. And to go with the sound, there's a movie of the changing sound spectrum. The movie also shows you the changing sky color and sound waveform. So here it is. Well, let's do that again, since it passes rather quickly. This time, you might also follow the little trackers for time and scale factor at the top left. Well, the primary impression is of a descending pitch. So what causes this? The effect is actually similar to first playing a violin, switching to a viola, and then a cello, and then a bass. The bigger the instrument, the deeper the sound. The dark matter clumps into which the gas is falling become larger at later times. What's happening is that as time passes, a sound wave can cross a larger and larger region, and so activate larger and larger dark matter regions. In fact, if you think of the universe as containing an entire set of organ pipes of all sizes, from tiny to huge, only those smaller than the sound horizon, that's the distance that sound can travel since the Big Bang, are actively sounding. As the sound horizon grows larger and larger, so larger and larger organ pipes are added to the register, and so the sound pitch drops. You may have noticed a more subtle effect. The drop in pitch slows down and stabilizes. This is because the sound speed is dropping and slowing the growth of the sound horizon. Now, the reason the sound speed is dropping is that atomic matter begins to weigh down the gas as light's power begins to wane. Ultimately, as the fog clears and the light can no longer push on the gas, the sound speed plummets and the sound horizon freezes, and the pitch also freezes. And ultimately, as we'll come to in Lecture 18, the oscillations cease and turn into a full-scale collapse to form stars and galaxies. So these evolving sounds are a necessary precursor to stars and galaxies. Let's end with a little more recreational fun and games by rendering these evolving sounds in musical form, with the harmonics artificially narrowed. Now, the frequency or pitch of each harmonic is plotted vertically with hertz on the left and a piano keyboard on the right. The time axis is exponential, so we have about 2 seconds for each factor of 10 in time. First is a version that includes the drop in pitch. And now the same version, but with the fundamental held fixed at 220 Hertz to help us hear the changing chord. Finally, let's force these frequencies onto the notes of our musical scale, which introduces a slightly artificial sense of rhythm as they shift to whichever note is closest. Now this, I'm afraid, is as close as it gets to something even remotely musical. Well, let's quickly summarize using these figures. The WMAP satellite creates an image of the microwave sky which, after suitable cleaning and stretching, reveals a myriad of brighter and darker patches, like rough water on an ocean. These are in fact the peaks and troughs of sound waves caught as they cross the wall of glowing fog that is the microwave background. An analysis of the patterns of patches reveals a broad sound spectrum with fundamental and harmonics. The pressure variations correspond to about 110 decibels, rock concert loudness, and the wave frequencies are 50 octaves below human hearing. Nevertheless, it's possible to upshift in pitch and play this sound. It's a rather rough roar. One can use computer simulations to access the pure sound and even generate its drop in pitch across the first 500,000 years. But the broad harmonics always sound rough to our ears. Now in the next lecture, we'll learn that slight differences in the properties of the universe lead to slightly different sound spectra. And so we'll see how cosmologists use the sound spectra to actually measure the cosmic properties. Now finally, however you reacted to hearing these versions of the primordial sound, amused or impressed or perhaps slightly disappointed, as we'll learn in later lectures, it had to be exactly that way if the universe was going to become the huge and stunningly creative place that it is.